If you're a systems operator, DevOps engineer, or any other profession that deals with modern infrastructure deployment, you've probably heard of Terraform and Instrctor as code. You may have done some research, or maybe even tried executing a few commands. If you're looking to dive deep into what Terraform is, how it works, and how it can help you manage and automate your infrastructure, you've come to the right course. We'll go beyond the basics of Terraform and delve into advanced features and functions. We'll get into details about HashiCorp Configuration Language, collaborate over Terraform configurations with remote state, and see how Terraform can work with popular DevOps tools to form an end-to-end deployment pipeline that tests not just your app, but your infrastructure as well. Throughout the course, we'll put you in command of Terraform, using it to meet real-world customer requirements and giving you the opportunity to experiment. This is an advanced course, so we'll be going beyond the basics of Terraform. You should already be comfortable with simple Terraform configurations, the Terraform CLI, and HashiCorp Configuration Language. We'll be deploying most of the sample configurations to Amazon Web Services. It will help if you have some familiarity with AWS resources such as VPCs, security groups, and EC2 instances. The sample configurations are on GitHub, so if you'll be following along, it will help if you have some basic knowledge of Git and GitHub. We won't be using any advanced Git features, just basic cloning and switching between branches. All you really need is a GitHub account and the Git command line tool installed. I'll demonstrate the necessary Git commands step by step. We'll be working with networking resources, so it will be good to have some understanding of IP networking, subnetting, and DNS. The EC2 instances we'll deploy will be Linux-based, and I'll be demonstrating Terraform usage in a Linux environment. Basic Linux usage and administration skills will be helpful, but not required. Integrating Terraform with other tools is a major part of advanced Terraform usage. We'll be combining Terraform with Jenkins and Terraform Cloud. You'll be able to use any experience you have with CI tools, but don't worry if you're not familiar with them. I'll explain as I demonstrate. Finally, Terraform is infrastructure as code, so you'll be able to apply any programming and software development experience you may have to Terraform. You certainly don't need software development experience, but a basic knowledge of programming in any language will give you a leg up. I'll be calling out cases where software development principles and practices apply well to developing and managing Terraform configurations. Let's take a few minutes and level set on the Terraform concepts and terminology that is the basis for this course. I won't be going deeply into each term. However, we all want to be on the same page so that when you hear me say configuration or deployment, you'll know exactly what I mean. Let's start with configuration. A Terraform configuration defines resources, variables, and values. A single configuration is usually a collection of several files. Complex configurations with a lot of resources usually include a larger set of files. Throughout this course, I'll use the term configuration to describe a set of files that is independently deployable, meaning I can open a shell in a folder, execute Terraform plan or apply, and Terraform will use the files in that folder to build a plan or execute the configuration. Here's an example. The source-controlled exercises project is a collection of configurations. It contains several configurations that we'll use to learn about Terraform. Each branch contains a separate Terraform configuration. HashiCorp Configuration Language, or HCL, is a domain-specific language developed by HashiCorp. By contrast with general-purpose languages like Java and C#, HCL is focused on defining Terraform configurations. HashiCorp developed HCL because static data files such as YAML or JSON lack the language features needed to make Terraform as versatile and adaptable as it needed to be. HCL supports basic language conventions such as variables, loops, and conditional operators. Terraform is primarily used to create instances of something in a cloud, provider, or other system. The general term for that thing is a resource. This could be a gateway in AWS, a Windows instance in Azure, or a configuration in a compatible load balancer. The resource reserved word is used to declare resources that will be created in the target system, such as a cloud environment. When an operator executes Terraform apply, Terraform executes a set of actions defined by a graph of resources. The set of resources created during this action is collectively referred to as a deployment. Terraform is capable of deploying and managing resources in several public clouds, including AWS, Azure, Google Cloud, and on-prem cloud managers such as OpenStack and VMware. These are just a few examples of the systems that work with Terraform. Terraform adapts itself to cloud and other systems using a provider. Providers are declared in a configuration and in turn make provider-specific set of resources available to that configuration. For example, using the AWS provider in a configuration allows you to declare AWS resources such as VPCs and EC2 instances. A module is an isolated, reusable sub-configuration. It cannot be deployed on its own, but it can be included in other configurations. Modules are used to isolate common configurations. Modules use input variables to define their behavior. If you've ever written a line of code in any language, you've almost certainly used a variable. Variables are named, typed containers of data. Older versions of Terraform supported only simple string variables. We'll be using the latest version, which supports a number of different types. That should set us up to talk more about Terraform. Let's move on. The exercise files for this course are stored in a repository on GitHub. If you don't have a GitHub account, you'll want to create one. This will allow you to create a GitHub-hosted copy, called a fork, of the exercise files repository. You'll need that fork for some of the course exercises. First, I'll show you how to create a fork, then you'll clone the fork to your local system. Create your account if you don't have one, then log into GitHub. Then navigate to the exercise files repository. This is the URL here. In the very top right of the screen, you'll see a button that says Fork. Click that button. GitHub will create a fork of this repository in your account. The next step is to clone your fork to your local system so you can work with the files. GitHub should navigate you to your new fork immediately after it's created. If not, click the GitHub icon at the top left and select the repo from the left list. If you just created this account, you should now only have the one repo in the list. Click the Code button and make sure it says Clone with HTTPS. Click the Clipboard to copy the URL to the clipboard. Now open a terminal window. You should be in your home directory. If not, execute cd space tilde on a Mac or cd space / on a Windows machine. Then enter git clone and then right-click and paste in the URL. Hit enter. If prompted, enter your credentials. Your fork of the exercise files will be downloaded to your local system. You should be able to open Visual Studio Code, go to File, Open, find the folder, click Open, and you should see these folders here. Great! We have our exercise files downloaded and we're ready to move on. We'll be doing a little role-playing throughout our journey with Terraform. You'll be taking on the role of an operations engineer at a consulting firm. Your job will be to help their client, Red 30 Technology, migrate an application from their data center to AWS. The first thing you'll need to do is to review the current state architecture of the application. For our purposes, we don't really need to know what the application does. Let's just assume it's an e-commerce application. We do need to know how it was built from an infrastructure perspective, so the Red 30's architecture team has provided you with an architectural diagram. The key parts include a load balancer to distribute requests between the front-end virtual machines, Linux virtual machines to run the service layer and front-end web application, and a MySQL database to store data. So this is a fairly typical multi-tier systems architecture, front-end, service tier, and back-end database. We're going to focus on the service tier virtual machines so we don't get bogged down in code, network, and data details that don't have much to do with Terraform. Now let's review Red 30's requirements. Requirement number 1. They want to migrate the application infrastructure to AWS using resources that are as similar as possible to the existing resources in the current architecture. This is known as lift and shift. The client wants to get their application migrated and working to AWS with a minimum of change to the architecture. The focus is to just get it moved and working. Requirement number 2. Improve resilience by isolating resources to availability zones. And requirement number 3. Maintain separate environments for dev, QA, staging, and production. The first task we'll need to take care of is to analyze the current architecture and create a Terraform configuration. That configuration must create resources in AWS that are analogous to the resources that support the application's current state architecture. This initial lift and shift configuration will become the basis of a more complex configuration that supports the client's additional requirements for resilience and multiple environments. Let's get configuring. Before we dig into Terraform configurations, we need to do some setup. I'll be using Visual Studio Code to edit the configurations, but you can use any text editor you like. I like Visual Studio Code, particularly for the integrated terminal. If you are using Visual Studio Code, open it, then go to the Extensions pane and search for Terraform. Install the one provided by HashiCorp. The first thing we'll need to do with AWS is to install the AWS command line tool. This is a useful utility that you can use to query the AWS API as you're working with Terraform. Navigate your browser to this URL, and then follow the instructions for your platform. I'm installing on a MacBook Pro, so I'll download the macOS package and then install. The next thing we need to do is to create an account in AWS. We'll be doing a lot of resource creation and destruction, so it's a best practice to use an account dedicated to that purpose while you experiment with Terraform. If you're using an account provided to you by your employer, ask your administrator to create you a separate IAM account. This will prevent accidental modification or destruction of resources that you didn't create. Open a browser and navigate to aws.amazon.com/console. Follow the account creation process, or if you're using an employer's AWS account, log in with the credentials provided to you by your account manager. Now you want to create a user that Terraform will use to authenticate to AWS. Once you're signed in, navigate to IAM. You can select it here from recently visited or search for it in the box here. And then select users. I already have some set up, so I'll just add another one to demonstrate the process. Click Add User. I'll call mine Terraform 4. You'll want to just use Terraform. And then select Programmatic Access. That will allow you to generate the access key and secret that Terraform needs to authenticate to AWS as this user. Click Next to go to Permissions. To make things simple for our demos, we're going to add this account to the administrators group. A word of warning, this is not a good idea for production deployment accounts. You'll want to limit their permissions as much as possible for production scenarios. Click Administrators, and then click Next. We don't need any tags, so click Next, and then click Create User. Now on this screen, we have the information we need for Terraform. This is sensitive data. The access key and secret are equivalent to a username and password. This is the only time AWS will allow you to see this data, so it's important to save it somewhere safe. Click Show on the access key, and then copy the key and secret to a file. We'll use them later. So what I just do is copy, and then you can return to Visual Studio and create a quick temp file just by double-clicking there, and you can copy that in. Then we can return back to the browser, go back to the secret key, make sure you get the whole thing without any extra spaces or anything. Copy that, return again to Visual Studio Code, and paste. Now we have that saved. Now we need to configure the AWS CLI. Open a terminal window and type AWS configure and hit enter. Now it's going to prompt for the data that it needs. So we're going to grab the AWS access key from the file, switch back over, and paste that in. Hit enter. Now it wants the secret key. Copy that whole thing. Make sure you don't get any extra spaces. And paste that in. Hit enter. We're going to stick with the default region I've set up, which is US East 2. You can change that if you like. And we're going to go with the default output format, which is JSON. Hit enter. Now we can test this by executing AWS STS get-caller-identity. If it works, you should see output that looks like this. You can see the ARN there is the identity for the Terraform user. Hit Q to exit. Now that we have the AWS CLI set up, we have one more thing we need to do before we can move on. We need to generate a key that we'll use for a future exercise. Open Visual Studio Code, open the exercise files, go to 0105 base, and open terraform.tfrs.backup. Here we have a command that you'll use to generate and download the key. If you're on a Mac or a Linux machine, you'll execute this first command. If you're on Windows, you'll use PowerShell to execute this one. So I'll demonstrate here by highlighting this command, flip back over to my terminal, paste it in, and hit enter. I'm just here in my home directory. We can do an ls, confirm that the key is there. We're good to go, ready to move on. The first thing we have to do to create a new configuration is analyze the current state architecture and determine which AWS resources we'll need. Some of them might be obvious if you're familiar with AWS. For example, the Linux virtual machines in the data center will become Linux EC2 instances in AWS. The load balancer will become an Elastic Load Balancer. Those are the easy ones, straightforward one-to-one relationships between AWS resources and the components of the system as documented in the diagram. There are elements of the application architecture that are not represented in this diagram. The diagram doesn't represent the network layer. It's up to us to make choices about how to implement a network design that will meet the client's requirements. Let's start by designing the new cloud-based architecture using the client's diagram as a template. So the Linux VMs become EC2 instances, and the load balancer becomes an AWS ELB. Now we need to define the networking elements that are not represented in the diagram. The next thing we'll need is an AWS VPC. A virtual private cloud is an isolated, software-defined network. We could use the default VPC, but it's more manageable to create dedicated resources. The VPC will define an IP address range that we can divide to create subnets. Speaking of subnets, that's another resource we'll need to define in our configuration. All EC2 instances must be assigned to a subnet. Our client's application is available from the public internet, so we'll need an internet gateway. This is an AWS resource that provides routing from the public internet to our VPC and its subnets. We'll also need a route table entry to route traffic from the gateway to the VPC. EC2 instances are part of a security group, which is like a software-defined firewall. When EC2 instances are created, they're added to the default security group. We can create and specify a security group ourselves. The security group rules determine which ports allow traffic on the instance's primary network interface. We'll need to open TLS ports to allow the application tier Linux instances running the front end to communicate with the public internet through the Internet Gateway. This is what our AWS infrastructure will look like, including all the elements from the original diagram and the networking elements we'll need to support Red 30's application. Let's take a look at our first Terraform configuration in Visual Studio Code. Open the 0105 base folder. This base configuration will create networking resources and deploy a single EC2 instance that could serve the application frontend or a service layer. We'll use this configuration as a starting point and make changes throughout the course, adding elements and rearranging the configuration as we evolve towards a complete production configuration. This base configuration has just two files, one main.tf for the configuration and a terraform.tfrs.backup file. Open the Finder and find the .pem file you saved during the AWS tool setup video, and then copy it to this folder. So we'll return to the Finder, find tf_.pem, copy it, and then open the repository, find this folder, and paste the item in. When we return to Visual Studio, we'll see the PEM file has been copied. The next thing we need to do is copy some values into this file here. First, make a copy of this file, terraform.tfrs.backup, and then right-click 0105 base and paste in a copy, and then rename this file to terraform.tfrs. So we'll just remove the copy backup here. Now we need to copy some values into this file. Return to the file where you stored the AWS credentials and copy in the AWS key and secret. Now we need to enter the SSH key name, that was tf_key, and the private key path, which is the path to the PEM file, tf_key.pem. Save that file, and we can move on. Before we dig into the configuration, I'd like to point out the .gitignore file. Terraform configurations deal with a lot of secrets. For example, the values we just entered for the AWS credentials into the .tfrs file. So I've used the .gitignore file to prevent the commit of several secret containing files. This will protect those secrets by preventing them from being committed to a Git repository where they might be discovered and misused. Let's take a look at the main configuration file. I've used comments to indicate sections of the configuration to make it easier to read. The first section is the variables. Using variables, we can create placeholders for values used by the configuration to deploy resources. We can define the values at execution time in a file or on the command line. Using variables, we can create a configuration that can adapt to a wide range of requirements just by setting their values. At the bottom of the file, we have output variables. Output variables are like return values. A configuration can have several or none. For our demo, we're going to connect via SSH to the EC2 instance, so for convenience, I'm outputting the DNS name of the instance, which is assigned by AWS when it's created. We'll see the value of this output variable in the terminal when we deploy the configuration. Scrolling back up to the top, we have the provider. We're using the AWS provider to demonstrate Terraform, but that's just one of many providers available. A provider is a plugin that provides an implementation specific to a cloud, a device, or a system that allows Terraform to create provider-specific resources. Our provider configuration defines values for the authentication keys and the region in which we'll create our resources. Note that these settings are set to variable values using the var.name syntax. The values are in the terraform.tf vars file. Scrolling back down, we have data resources. These are data resources. Data sources in Terraform allow a configuration to query for external data. We have two data sources defined here. One to get the list of availability zones in the region defined in the provider. For me, that's US East 2. And the second data source gets a list of AMIs. An AMI is an Amazon machine image, and they're used as the basis for EC2 instances. The filters in this query return the one we want to use for our EC2 instance. The next several sections of main.tf will define our networking. First, we define a VPC that will create a software-defined network for us to work with, so that comes first. All the other networking resources we create will be within that VPC. Our two VPC settings are the CIDR block, which is required, and a setting that will create DNS entries automatically for EC2 instances created within the VPC. The DNS setting is for convenience while we demo. Typically, individual instances would not have their own DNS entries. CIDR stands for Classless Interdomain Routing. CIDR block notation looks like the setting for our variable here, 172.16.0.0/16. This format defines a starting IP address and a number of bits for the subnet mask. This notation defines a network starting at 172.16.0.0 with 65,536 hosts. We'll use that address space to define the subnets for the EC2 instances. And speaking of subnets, here's one now. Our configuration starts with a CIDR block for the subnet. Referring back to our variable value declarations, note that the subnet CIDR block is a subnet of the VPC CIDR block. The larger /24 block defines a 256 host subnet starting at 172.16.0.0. This is the subnet we'll use for our EC2 instance. The instance we're creating is going to host a front end, so we need to set it up with public internet access. This is done in AWS with an internet gateway. The only value we have to define on this resource is the VPC ID. Note that the value provided here is the ID of the VPC, not its name. The syntax indicates the AWS VPC resource, then the local name VPC1, and then the ID property. Terraform takes care of populating this value for us after the VPC is created so we can use it elsewhere in the configuration. In order to route traffic to and from the subnet we defined to the internet gateway, we'll need to add an entry to the route table. This resource refers to our VPC and then defines a route section with two values, CIDR block and gateway ID. The all zeros CIDR notation here indicates any subnet within the VPC. The gateway ID value is set to the gateway we defined above using the same syntax used to get the VPC ID. Note that the route table resource definition does not specify our subnet. To create the relationship between our subnet and the route table entry, we use a route table association. This next resource simply associates the route table entry with the subnet using their IDs. We're almost done with the networking configuration. The last resource we have to define is the security group. The security group is a software-defined firewall that sets port ingress and egress rules directly on the primary network interface of any EC2 instance to which it is assigned. The front-end instances will need public internet access, so we need a few ports open. We'll open port 80 and 443 to support HTTP and TLS traffic. For demo purposes, we're also going to open port 22 to support SSH. As we evolve this configuration, we'll remove this setting from our production app tier instances. Note that we can define multiple ingress stanzas, one for each port. Each stanza defines attributes. From port and to port can be the same, or define a range of ports. Protocol can be a value like TCP, UDP, ICMP, or other Internet protocols. CIDR blocks is a CIDR notation defined range of IP addresses to which the rule will apply. Again, we have all zeros here, which indicates all IPs. Now we've reached the meat of the configuration, the EC2 instance itself. This EC2 instance has quite a lot going on. We define the AMI we want to use by its ID. This is coming from the data resource we defined below. We have the instance type, which will determine how much processor and memory the instance will be allocated. We have the subnet we defined. We have the security group, which you can see is a list indicated by the square brackets. We'll talk more about data types and lists later in the course. And finally, we have the name of the key we generated in the AWS setup. This key will be pushed to the EC2 instance when it is created, allowing us to connect via SSH. All right, we're ready for our first deploy. I'm going to demonstrate the Terraform CLI using the integrated terminal in VS Code. So we can go to Terminal, New Terminal, and that will open a new terminal in this window here. Our first step with this configuration is to initialize it. This command prepares a configuration for all other Terraform commands. Initializing will download the AWS provider, which is listed in the main.tf file. Configurations can have multiple providers, by the way. The init command will download all defined providers anywhere in the main configuration. This is also known as the root module. We'll get more into that later. So we'll execute Terraform init. First, we need to change directory into 0105 base. Then we'll execute Terraform init. And the output says that we're initialized and gives us the AWS provider version that we've downloaded. The init command has made a change to the contents of our configuration. You can see that we now have a .terraform folder here, and it contains a lock.json and the provider binary. The binary is the provider itself, and the lock.json file is used by Terraform to manage providers. The next step to deploy this configuration is to create a plan. Cloud resources have dependency relationships between them. Subnets relate to VPCs, instances relate to security groups, and so on. Terraform represents these relationships in a dependency graph. Terraform needs the graph to know which resources to create first, so that resources that depend on them can be created after. Return to the terminal. We're going to output the plan to a file. Terraform plan-out equals s1.tf plan. Terraform outputs the plan both to the console and to the s1.tf plan we specified with the -out parameter. Operators and users of Terraform use plans to review the changes Terraform will make before they're executed with the Terraform apply command. Expand this a little bit so we can see it more clearly. And I'm going to scroll up to the top here so we can take a look at the plan. This is a brand new, undeployed configuration, so all the actions Terraform will take will be creation actions. This plan will be applied in reverse order. The first resources created are at the bottom, so let's start there and work our way up. All the resources created in this configuration depend on the VPC, so that is created first. Then we see the subnet, and we have the security group, route table and the associations, the internet gateway. If we keep going, we get to the instance. We can see the dependency graph described by this plan by executing Terraform graph. The output is a digraph, which we can take to www.webgraphviz.com and generate a visualization. So I can copy this content to the clipboard, open a browser, and I can paste the digraph in here and hit Generate Graph. This is a fairly simple configuration, so the graph view is nicely readable. Visualizations for more complex configurations get rather busy and harder to read. So we'll return to Visual Studio and get back to our terminal here. Let's suppose that you're collaborating over a configuration and you want to view the contents of a plan generated by someone else. The .tf plan file is a binary file, so we need the CLI to view it. If I were to click on that file here, s1.tf plan, you'll see Visual Studio says it can't open it because it's a binary file. So we can execute Terraform show s1.tf plan. This will output to the console the same data that was displayed when the plan was generated. The format is designed to be human readable. We can also generate machine readable JSON. Terraform show /JSON s1.tf plan. This is especially useful when integrating Terraform with other tools. Terraform is often incorporated into a CI/CD pipeline. JSON formatted plans can, for example, be imported into a visualization tool or read by a step in a pipeline to send alerts. The possibilities are endless. All right, now we're ready to deploy. The command is simple. Terraform apply s1.tf plan. This command will read the plan and execute it. The provider reports each step as it completes. Remember the output variable in the configuration? The DNS name of the instance is generated when the instance is created, and Terraform applies the value to the public_DNS attribute. That's over here in the main.tf in our output variable. The value is then output at the end of the apply with this output variable. This will take a moment to run, so here we go. And we have the instance-DNS output variable has reported the DNS entry for the instance that we just created. Our last step is to SSH into the instance. This is really just for our demo. There are automated steps that we could take to validate that our configuration was successful. We wouldn't normally use SSH for that in a production scenario. First thing we need to do here is make a change to the key. So chmod 400 tf_.pem. We have to have specific permissions on this file for SSH to work. Okay? And now ssh-i tf_key.pem and then ec2 user-user at, and here we're going to copy the DNS address of the EC2 instance and paste it in. Type yes, and we're connected. I can demonstrate by listing here, we're empty, list the root. Here's the contents of the root of this EC2 instance, so we're connected. I can execute who am I, show that we are EC2-user, that's part of the configuration. And finally, we can type exit to exit the session. Before we move on, let's take a look at the state that Terraform is tracking for our configuration. The resources in a configuration represent resources that will be created when that configuration is deployed. During deployment, actual resources are created. Terraform stores a record of the state of those deployed resources. By default, that state file is stored locally. Execute Terraform show with no parameters. By default, the show command displays the state. Terraform maintains the deployed configuration state in this file. Whereas the plan is a binary file, the state is a plain text JSON file we can inspect in Visual Studio Code. So we can go here to the terraform.tf state file and see that it is just plain JSON. Terraform keeps the state separate from the actual deployed resources. We can see in these resource definitions that they all have their attributes populated, whereas in the plan, these values are mostly listed as known after apply. For example, the ID of the instance is generated when it is created. The actual value is present in the state. When changes are made to the configuration, Terraform uses the state to compare against the resource graph of the updated configuration. Differences become actions that Terraform will take to converge the desired state represented by the configuration against the actual state represented in the state data. Let's take a quick look at the resources we deployed using Terraform in the AWS console. We can go to the VPC section, go to the list of VPCs, and see that our VPC is here. The subnets that we created are right here. The route table is here, and the internet gateway is listed here. We can also see that it's assigned to our VPC, and you can click the links here to navigate back and forth between resources. We can go to the EC2 dashboard, go to our list of instances, and see the instance listed here. It has an IP address in the range that we assigned it, and it has a security group associated, which you can see here. And if we look at the details, we can see the ingress and egress rules that we set. We can imagine how tedious it would be to create and manage all this configuration through the console, and that's the magic of Terraform. We can declare the resources we want by configuration, check that into a repository, and iterate over it as we would with code. There's also a faster way to check on resources using the AWS CLI. I'll return to Visual Studio, execute this command with AWS. AWS EC2 space describe dash instances dash query, and then in quotes, reservations, open close square bracket, dot instances, open close square bracket, dot instance ID, and then output table. you'll see a single ID listed in the output for the one instance that we created. By the way, the output here uses the less pagination system. If you don't like that, you hit Q to exit and then type export AWS_pager equals double quotes. And then you can execute it again and it will just output to the console and return. If you like this mode better, you can add that export command to your bash profile or whatever shell you're using. The last thing we need to do is clean up after ourselves. So here in Visual Studio Code, we're going to execute Terraform destroy. This command does what you would expect. Destroy all the resources defined by the configuration. Terraform will display the changes it will make and asks us to confirm explicitly by typing in yes. This takes a moment here to run, so we'll let it go. Then we have to enter yes in order for it to destroy these resources. This will remove all the resources created by this configuration. Just as Terraform knows the order in which to create, it can use the reverse order to destroy our deployed resources. This is by definition a destructive process, so proceed carefully when working with Terraform. Removal of resources from higher level environments, especially production, should be handled with extreme care. The destroy command should never be used in a production environment. It's a much better practice to remove resources from the configuration and apply the change, selectively destroying only the resources that should be removed. Let's also talk for a moment about AWS free tier resources. Amazon offers 750 free hours per month of a single T2 micro instance. If we look in our configuration here and go to the instance, you can see that we're using T2 micro as our instance type. This is equivalent to one instance running 24/7 the whole month, or two instances running side by side for 325 hours, etc. It's important that you remember to clean up any resources you create throughout this course with Terraform destroy so that you don't run out of free time. Also, keep in mind that if you choose to create anything larger than a T2 micro as you experiment, you may incur charges to your AWS account. As I demonstrate Terraform deployments throughout the course, I will always remind you when it's time to remove the resources after we're finished with an exercise. This can always be done with the Terraform destroy command, as long as the state file is available. However, mistakes happen. The destroy command will not work if Terraform created resources are modified outside Terraform or if the state file is missing or corrupted. If you find, for any reason, that you're unable to run Terraform destroy, you can remove Terraform deployed resources manually through the AWS console. A note of caution here. It's best to have your AWS administrator create a dedicated sub-account for your experimentation, so that all the resources in that account will be the ones you create with Terraform. If that's not possible, and you're working in an account with pre-existing resources, be extra careful as you remove the resources you created. Make sure you're selecting only the resources you created with Terraform and no others. I've deployed the example from 0105 base. Here in the AWS console, we see one VPC, and if I go to the EC2 section, we see a running instance. Returning to the VPC section, you'll see that if I attempt to select the VPC and then delete it, actions delete VPC, I get an error. I have resources running that depend on this VPC. I can click the instances link here, find the EC2 instance, and remove it by right-clicking, go to Instance State, and select Terminate. Click Yes. And that will terminate the instance. While that's working, I can return to the VPC tab here, and this network interface is actually the network interface of the Internet Gateway. I'm going to click Cancel, select Internet Gateways, select the attached Internet Gateway, go to Actions, and select Detach from VPC, and then click Detach Internet Gateway. I have one more thing I have to remove. Go to Route Tables, find the route table ID with an explicit subnet association, select it, click Edit Subnet Associations here below, and then click this X. Click Save, and then return to the VPC section. It may take a minute or two for the instance to terminate and the gateway to detach, so you may need to attempt the deletion several times. Select the VPC, click Actions, and go to Delete VPC. When you see this screen here, it means we're ready to delete. Type delete into the field and click delete. When this is complete, we should see no VPCs. We're all cleaned up and ready to move on. Computer programs use variables to adapt a generalized program to a specific application. This is what makes it possible to write a single program that can handle a variety of situations based on the data fed into it through variables. Terraform uses variables for the same purpose. We can create a general purpose configuration in Terraform and adapt its deployment behavior using variable values. Variables can be fed into a configuration when it is deployed. These are called input variables. The values of input variables can be set in a variety of ways, and there's a hierarchy. Terraform will use the value first in an environment variable, then in a file such as terraform.tfrs or any file ending in .auto.tfrs, and then the command line in that order of precedence. The command line will override a file, and the file will override an environment variable. If none of those methods are used, the variable will take on the default value if declared in the configuration. If no value is set by any of these methods, the value is null. After a Terraform apply operation, Terraform can report the value of variables to the console. These are called output variables. We've seen an example of output variables in a previous chapter with the instance DNS name. Terraform variables also have data types. Older versions of Terraform only supported strings. Newer versions, including the one we're demonstrating, support 3 primitive types and more complex types. Terraform has always supported the string type. The version we're using also supports Boolean, which is true and false, and the number type supports integers and fractional values. Terraform also supports collection types using type constructors. A list is a zero-based indexed array of variables. The order of its members are set when the list is instantiated, and the first index is 0. All of the elements of a list must be of the same type, and the syntax for accessing a member is var.variablename, and then the index you want in square brackets. A set is similar to a list, except that the members are not in any particular order. A map is a lookup table of key-value pairs. The keys are strings and must be unique to the collection. The values can be of any type, but all of the members of a map must be of the same type. Then we have structural types, like objects. An object is like a struct in C or Java. It's a collection of named attributes. The attributes can have different value types from each other. For example, here we have variable instance settings, and it's an object with 2 members. The first member is called instance type, and its value type is string, and the next one is monitoring, and its type is Boolean. We also have tuples. Tuples are similar to objects, but they have stricter type conversion rules. Throughout the course, we'll be sticking with objects. We won't be using tuples. Let's look at how variables are declared in a configuration. Open the 0201 variables folder and find main.tf. Open that up. The next thing we'll need to do is create a copy of the terraform.tfrs.backup file, paste in a copy into that folder, and rename it to terraform.tfrs. Now we'll need to get the access key and secret key for AWS. You can get that from the file you created in the setup video for AWS, or if you've done the previous chapter, you can find it here in terraform.tfrs under 0105 base. Copy the access key, paste that in, and then the secret key. Make sure you get the whole thing without the quotes. Paste that in, save the file, and return to main.tf. The first few variable declarations here determine the key values to authenticate to AWS. The curly braces are empty, so they have no default value and will be of the default type, which is string. The next several variables do have default values. We've seen how the .tfrs file can set variable values. If there's no default set for a variable and no other method is used to set the value of the variable will be null. The Terraform CLI will prompt for null values when the plan command is executed. The variables we've used so far have all been string types. Let's take a look at some examples of the other variable types I mentioned earlier. Here on line 20, we have an example of a list. This list is used to store a name for all the environments to which this infrastructure will be deployed. The dev environment is the first shared environment to which we'll deploy. The other environments are used for more advanced testing, and prod is the environment where end users interact with the system. This data type is useful in situations where a configuration needs a single variable to store multiple values. Suppose that we want to add a tag to the resources we're creating. Tags are useful for adding metadata to resources, which can be used for reporting purposes. So if we scroll down to the EC2 instance, we can see that we have tags equals, and then in curly brackets, environment equals var.environment list, and then the 0 in square brackets, which is the first element of the environment list. So here this will create a tag with an environment key and the value of environment listed 0. If we scroll back up to the variable declaration, we can see that that first element is the string dev. You might be thinking, why not just set that value directly? We could do that, but the benefit of using a variable is that it makes our configuration flexible. If I need to change the value throughout the configuration, I can change the value there on line 22 and it flows through every other setting. Let's take a look at how this affects what will be deployed. Go to your terminal, change directory to the variables chapter folder, and then execute Terraform init. This will download the AWS provider and prepare our configuration for other commands. Now execute Terraform plan -out equals s1.tf plan. This will generate the plan and display it. Now if I scroll up to the instance definition in our plan, we can see that we have a tag where the name of the tag is environment and the value is dev. If you don't want to remember a numerical index, you can use a map instead. Here on line 25, we have a map type, environment map. The map uses a string value index instead of a zero-based numerical index. You could use the map the same way to set the value. So if we scroll back down to the instance, I could change environment list to environment map at dev. Save the file. Go back to the terminal here. Generate the plan again. And once again, I can scroll up the instance and we can see that the tag environment is still set to dev. Now let's take the map type a little further and use it to vary other parts of our instance. EC2 instances have an instance type attribute that determines its CPU and memory capacity. We're using the t2.micro instance type because it's in the free tier. Scrolling back up to our variables here, we can find environment instance type. We can use the environment instance type map variable to associate the environment name with the instance type we want in that environment. I've set them all to t2.micro so we don't accidentally incur any unintended costs. I'm using that variable to set the instance type. So if we go back again to the EC2 instance type and look at that value, we can see instance type equals var.environmentInstanceType at dev. The key dev stores the value t2.micro. Once again, this makes our configuration easy to modify. If the ops team comes to us and says our production servers are underpowered, which they most certainly would be at T2 micro, we can upgrade them by modifying one variable value and then redeploy. This map variable provides the flexibility to support different instance types in different environments. Now let's use the object type to take our variables one step further. Remember, all the members of a list or map must be of the same type. Objects can define a schema with multiple types. Instance type is not the only thing that might vary from one environment to the next. For example, when set to true, the monitoring attribute of an EC2 instance enables enhanced monitoring. You might decide that detailed monitoring is worth the additional expense in production instances, but not necessary in other environments. The environment instance setting variable is a combination of two types, map and object. It's a map of objects. The key value type for maps is always a string, but in this case, the value of each element is an object with a predefined schema we can see here on line 46. That determines the name and types of the object members. We can now go to the instance resource definition and look at those settings there. So in the instance here, I have it commented out. So we'll comment out this instance type and uncomment this one. And that's using our environment instance settings. So we see the instance type is set to var.environmentInstanceSettings. Using our key, this time I'm using prod, and in the dot notation accesses the member of the object. So if we go to our instance definition, we can see that we have one key for each environment and then two members, instance type and monitoring. So we can access any one of these individual settings here, these elements, using this syntax var.environmentInstanceSettings, the key we want, and then dot, and the member of the object, instance type. We can also see that we're also doing that same thing here for the monitoring attribute. Monitoring equals var.environmentInstanceSettings. Once again, our key is prod, and then dot monitoring. The monitoring attribute is a Boolean. This makes for a very readable, flexible way to store any number of settings in a single variable. You can combine list types, lists, sets, and maps in many different ways. For example, an object can have list type members, and a list can be populated with objects. This flexibility gives you lots of options to shape the data you feed into your configurations to adapt their behavior. Let's use what we've learned so far to make a change to the variables exercise. The deployment environment of the EC2 instance here has been hard-coded. That's useful for experimenting, but in a production-ready configuration, we should be able to define the environment we want to deploy when we generate our plan and apply the configuration. That's a perfect case for a variable. See if you can make the changes to the configuration on your own. Here are the requirements. Declare a variable called deploy_environment, give it a default value of DEV, and then modify the EC2 instance to use the value of deploy environment. Here's a hint. The changes you'll need to make to the EC2 declaration will be between square brackets. Pause the video and see if you can make the change. Then generate a plan with Terraform plan. Don't worry about deploying, just see if you can generate the plan and display it. When you're done, return to this video and we'll walk through the changes together. All right, welcome back. So let's enhance this variable's example and drive our configuration by environment. So we're going to declare our variable, deploy environment, add our curly braces, and then set our default value. Now we can go change the EC2 instance declaration. Okay, so we can see here that instance type, monitoring, and the tag value here is being set hard-coded to prod. This is what we'll need to change. We can set this setting here to var.deploy environment, and IntelliSense helps us out there a little bit. Let's change it there as well. And finally, we'll change it here. Change that and then save the file. Okay, now we can generate the plan. Terraform plan out.s1.tf plan. And while that's going, I can show you here in the map variable and the list variable, environment instance settings, we have our instance settings for the instance type and the monitoring. We can see they're all the same here except for prod, where monitoring is true. So we've just used the default value for the variable, deployment environment, and we can see in the instance type here, it's set to T2 micro, monitoring is false, and we have our tag. Now, we've said before that we can override a variable value at the command line. So let me demonstrate that now. Terraform plan -var, and then we can set the value, deploy environment equals prod. I'll execute that. This won't save it to a file. It'll just export it out to the console. And let's go take another look at that EC2 instance with this run. We can see that the instance type is still T2 micro. We can see that monitoring is now true. And if we go to the tag, the environment is prod. So that's an example of how variables can be used to adapt the way that a configuration is deployed. Let's talk about how variable values are set within a configuration. We've already seen one way, the .tfvars file. The .tfvars file is a variable definitions file. Terraform will automatically read a file named exactly terraform.tfvars or terraform.tfvars.json and use its contents to set variable values. If terraform.tfvars.json is present, it must contain JSON formatted data. Terraform will also process any file ending in .auto.tfvars. This means that multiple variable definition files in a single configuration can set variables. This is useful in a number of situations. For example, in a complex configuration, some variables might affect network resources, while others affect instances. By controlling access to multiple files, such as network.auto.tfvars or instances.auto.tfvars, multiple teams can collaborate over a shared configuration. The network ops team can set values for network resources, and the app team can set values for EC2 instances. Environment variables are yet another way that variable values can be set. Terraform will inspect the local system for any environment variables whose names are prepended with tf_var_. The name after the second underscore is the name of the input variable to be set, and that variable value is set to the value of the environment variable. Finally, The value of a variable can be set at the command line using the -var and -var-file parameters. The -var parameter sets a variable value directly. The -var-file parameter can direct Terraform to process a variable definitions file that doesn't conform to the variable definition file naming conventions. Each of these methods work to set variable values, and they have an order of precedence. First, environment variables, then terraform.tfvars, then terraform.tfvars.json, any.auto.tfvars file present, and finally, the -var and -var-file command line options. Any variable definition sourced later in the list will override settings earlier in the list. As you can imagine, this can get complex, so it's generally a good idea to settle on a variable definition strategy that includes as few sources as possible to keep things simple. This precedent system can be useful to establish defaults that can be then overridden in specific circumstances. A word of warning about using environment variables. When hackers compromise a system, environment variables are one of the first things they look at to find valuable information. This makes it risky to store secrets, such as the AWS key and secret, in environment variables. The best practice for setting secrets as values in Terraform is to use a file, or even better, a command line parameter. Computer programs typically have return values that report the status of an operation. Terraform output values are like the return values of a configuration. The configuration we've been working with already has one output variable defined here, the DNS name of the instance we're creating. Output values have a name, which can be any string, and a value. The value can be any setting in the configuration. Here we have a common pattern we've seen throughout the configuration. This is called a triplet. We have the resource type, the name, and then the attribute. Let's dig into some more possibilities. If you haven't already set up this exercise, there's a couple things you'll want to do to prepare it. First, make a copy of terraform.tfvars.backup and copy that into 0202-07 variables and then rename it to terraform.tfvars. Then you'll want to get the AWS access key and secret. That's from the file you created in the AWS tool setup video or from a previous exercise, like up here. Copy the AWS key and secret to terraform.tfvars here in this exercise. Then in the terminal, change the directory to 0202-07 variables and execute terraform init, and then execute terraform plan-out equals s1.tfplan. If you have already initialized this exercise and already have a plan, you can use this command, terraform show s1.tfplan. That will just output the plan again to the console. So once we have the plan displayed here, we can see that most of these settings here are listed as known after apply. Terraform won't know what these values are until the configuration is deployed because those values are assigned by AWS when the resource is created. Let's deploy now and use the show command in a different way. So execute terraform apply s1.tfplan. All right, and now we're all deployed. Note that the last output to the console here is the value of the instance DNS output variable. Now let's look at the values that were assigned to all these resources. Let's execute terraform show, but this time with no parameters. The show command is now displaying the contents of the state of the configuration instead of the plan. The state contains all those values that were assigned by AWS. All of these values are available to Terraform after the apply command completes, so any of them can be the value of an output variable. Let's try that now. Suppose we want to output the internal DNS name of our instance. We can find that by scrolling up and finding it in the instance definition. So if we go here and look at the EC2 instance, here it is, private_DNS. So let's go to the configuration and add a new output variable. We'll give it a name. Open curly brackets, value equals, and once again our triplet, AWS instance dot node.js1 dot private DNS. Save the file. Now let's go back to our terminal and execute terraform destroy so we can start over. It will prompt us to enter yes here. Go ahead and do that. And now we're all cleaned up. We can start over. So now let's execute Terraform plan dash out equals s1.tf_plan. This will regenerate our plan. And now let's redeploy Terraform apply s1.tf_plan. And now we're all deployed. And this time you can see that we have two output variables, one for instance DNS and one for private DNS. Output variables are useful when combining Terraform with other automation systems like Jenkins. The values can be used in later stages of a larger job. Output variables can also be used by a completely separate configuration when they're using remote state. We'll talk about remote state later in the course. Okay, now finally, let's make sure we clean up. Terraform destroy, so we don't leave these resources running. Enter yes when prompted, and we're all cleaned up and ready to move on. Developing configurations in Terraform is similar to developing software. HashiCorp Configuration Language, which I'll call HCL from here on, is a domain-specific language, or DSL. DSLs are limited languages that share some, but not all of the features of a fully featured language like Java or C#. Fully featured languages support expressions and functions. HCL supports expressions and a library of predefined functions. An expression is a statement that can be evaluated by the Terraform CLI. This can be a simple literal value, mathematical and conditional statements, or calling a Terraform function. HCL does not support user-defined functions. Instead, Terraform includes a set of predefined functions. Terraform functions allow for things like string manipulation, working with data structures, IP subnetting, and more. So for our demo, we won't be deploying yet, so you don't need to worry about setting up the .tfvars file just yet. Change directory to 0208 to 9 expressions functions and just execute terraform init. Now let's use a new command to experiment with expressions and functions. Terraform console. This command starts an REPL, or REPL, which stands for Read, Evaluate, Print, Loop. A REPL is an interactive program that accepts input, evaluates it, and prints a result. The loop is the prompt for the next input. Our Linux command prompt is an example of a REPL, as is any interactive shell or program that accepts input in this way. We can use the console REPL to experiment with expressions and functions. The commands we execute here will work exactly the same as they would if they were part of our configuration. Let's start simple. I'll just type 5 and hit enter, and then hello in quotes. These are literal values, just a number and a string. The Terraform console REPL just echoes their values back to us. Now let's try some math. 5 plus 1. 6 divided by 3. 3 times 5. We can see that the REPL evaluates these as mathematical expressions and returns the result. Now let's try some basic logical operators. 3 is less than 5. 3 is greater than 5. 3 is equal to 5. And 3 is not equal to 5. So we can see that these logical operators simply return true or false depending on the expression. For our last trick, we have some basic support for conditional logic. I'm going to enter 5 does not equal 5 question mark, open quote foo, close quote, colon, open quote bar, close quote. This is called a ternary operator. It's like an if statement, but it can only return a single result, as opposed to a fully featured language executing a separate branch of code. If the conditional part is true, then the first element after the question mark is the result of the operation. If false, the second element after the colon becomes the result. So 5 is not equal to 5 is false, therefore bar is the result. So Terraform and HCL support some of the essential features of a programming language, including basic expression evaluation. Terraform also supports a library of functions, which are built into Terraform. Terraform functions are grouped by type: numeric, string, collection, encoding, file system, date and time, hash crypto, IP networking, and type conversion. Each type here has a library of functions associated with it. Let's take a look at some examples. So returning to the 0208 to 9 expressions functions folder. Now we are going to deploy this configuration. So the first thing you'll need to do is get the terraform.tfvars file from a previous exercise, or you can create a copy of the .backup file here, paste it into the folder, rename it to terraform.tfvars, and copy in the AWS access and secret keys that you generated in the AWS setup video. In your terminal, change your directory to the 0208 to 9 expressions functions folder. Then we execute Terraform plan-out s1.tf plan. This will generate our plan. And finally, Terraform apply s1.tf plan. And this will deploy our configuration. Okay, now let's take a look at a few function examples in action using Terraform console. So execute Terraform console. That will bring us into the REPL. The console command starts a read, evaluate, print loop, or REPL. A REPL is an interactive program that evaluates input and returns a result. Functions have a name like split and 0 or more parameters. Functions return a single value of varying types depending on what they do. Here are some string function examples. Length, Terraform. Upper, Terraform. And now split. 1, 2, 3, separated by commas. These functions do what their names suggest. Length returns the length of a string, so there are 9 characters in the word Terraform. Upper converts text to uppercase, and there's a lower function that does the opposite. And split uses a character delimiter to split a string into elements. The split function returns a list type. There's also a join function that does the opposite of split, so we can do join, our delimiter, and this time we'll give it a list. And that returns a string delimited by the comma. The console can also read from the configuration state. Let's exit the console real quick and take a look at that state. Exit. And then Terraform show s1.tf plan. This is the plan we created earlier in the chapter. Note that all these entries say known after apply. The plan includes the resources in the configuration, but the values for these attributes are assigned by AWS when the resources are created with Terraform apply. Now let's execute Terraform show with no parameters. This command displays the state. The state was saved when we executed Terraform apply. The state contains all the values created by AWS when the resources were created. Terraform uses the difference between the plan and the state to detect changes to the configuration, which in turn is used to generate a new plan that deploys those changes. The values in the state are all available to the console. We can enter one of these resource identifiers, resource type.name, and Terraform will display the block of attributes for that resource. We can also get a single value by entering the full resource triplet, type.name.attribute. So let's take a look. Terraform console. Now we can enter AWS underscore VPC dot VPC1. If you were to scroll up here in the state, you would see that we have a lot of information about that in the state. We can execute this here, and it returns us a JSON block of the state that was created when we deployed the configuration. We can do it again. AWS underscore instance dot Node.js1. Again, this is an entire resource declaration, so it's going to return all the attributes for that resource. And then we can get a single scalar value. AWS underscore instance dot Node.js1 dot public IP. Calling these elements of the state outputs them to the console. These values are accessible to functions as well. So let's take a list type, for example. Data.aws underscore availability zones dot available dot names. This is a list type. Okay. These are all the zones available in the US2 region. Now let's try this. Join using a string, and then once again, data.aws underscore availability zones.available.names. And we get back a string with those zones delimited by commas. This is a great method for testing HCL statements and expressions to confirm that they work the way you intend them to. As always, we need to remember to clean up after ourselves when we're done with the configuration. Execute Terraform destroy to clean up our deployment. Enter yes, and this will remove our deployment so we don't keep it running. So far, our configuration has created only one EC2 instance, AWS underscore instance.node.js1. This is great for demo purposes, but you can imagine we're going to need more than that for any real application with a production load. What to do? Let's suppose we want to create 4 EC2 node instances instead of just one. It would be very inefficient, not to mention difficult to maintain, to create 4 separate resource entries. It would work, but it's not the best way. Fully featured languages use the concept of loops to perform code iteratively. Terraform doesn't have loops per se, but it does have a mechanism to repeat a resource creation multiple times. The count and for each meta arguments. First, let's prepare the exercise for this chapter. Open the 0 to 10 count folder and open up main.tf. And now let's create a copy of the terraform.tfvars.backup and then paste that copy back into the folder. Rename this file to terraform.tfvars. And then from a previous exercise or from the file you created earlier in the AWS setup video, find the AWS key and secret and copy those in and save the file. And now in the terminal, from the 0 to 10 count folder, execute terraform init. And we're ready to move on. So let's experiment with count. In the main.tf file, in the exercises, find the instance, and we'll work with that. So let's uncomment this line here, count equals 4. And our resource name here, node.js1, is no longer a single instance, so let's give it a more appropriate name. We'll call it node_instances. That's a better name to describe a group of EC2 instances running the Node.js web server. The count meta argument can be set to a whole number, an integer. Adding this line will cause Terraform to execute this resource deployment exactly 4 times. Each instance will have its own state entry, just as if we'd added 4 separate instance declarations. Now let's try to create a new plan. Go to the terminal and execute terraform plan -out equals s1.tf plan. We're getting an error with our output variable. Why is that? Well, the first reason is that it no longer has the right resource name. Let's fix that and try again. So we change the name here to node_instances. So we'll need to update that. Go down to the instance output variable here, and let's change it to node_instances. Return to the terminal, and we'll try again. So we're still getting an error. The name is correct, but the variable refers to a resource block that uses count. There's no longer a single value to access. There are 4 separate resources being created. So here's the fix. We're going to add .star to this declaration here. The star character is called a splat expression. Let's regenerate the plan, and then I'll demonstrate how the splat expression works when we deploy. So terraform plan -out equals s1.tf plan. Now let's take a look at how for each works. You may have noticed when we set up the .tfvars file here that we have an extra variable that we haven't seen before. This is a set type variable with a list of names. We'll use that to demonstrate for each. So let's suppose we want to create a list of IAM accounts with this deployment. The count argument is good for creating identical resources. These IAM accounts will each have a different name. The for each argument can iterate over sets and maps and take action for each member of those collection types. So first let's add the resource. I'm going to go back over here to main.tf. I'm going to find our instance, and we'll add a new resource below that. This will be resource AWS_IAM_user. This is an AWS resource type. IAM-users is just going to be the local name, open curly bracket. Now the first line here is going to be for each equals var.IAM_accounts. That's the name of our variable. And then the attribute we're going to set is name, and it's going to be set to each.key. When for each is used in a resource block, it makes a special value called each available to the block. We're using a set here, so the members of the set are accessed by each.key. When using maps, the value of each member is also accessible using each.value. Now let's generate our plan again and take a look at what will be created when this configuration is deployed. In your terminal, terraform plan -out equals s1.tf plan. So if we scroll up, I'll make a little more space here so we can see it more clearly. If we scroll up in this plan, all the way to the beginning, we can see that we're creating one IAM user for each member of the set in IAM_accounts. And if I scroll down a little further, you can see that we're creating 4 separate instances. Instances at 0, instances at 1, instances at 2, and so forth. So now let's apply the plan, and we'll deploy. Terraform apply s1.tf plan. And our instances are now deployed. You'll notice here that the output value is a list instead of a scalar value as it was before. Let's take a quick look at the state. So execute Terraform show. Let's scroll up to the top. We see that there's a comment with a hashtag above each instance. Scrolling down, we see that each of the instances are labeled AWS_instance node_instances. Terraform merges these together into the one name so that we can refer to each instance attribute as a member of a list. That's how the splat works. It refers to a resource that was created using count or for each. So Terraform provides count and for each to make it easy to perform a sort of bulk resource creation. Count is good for identical resources, and for each is ideal for resources that vary one from another. As usual, let's clean up our deployment with Terraform destroy. A Terraform module is a self-contained encapsulated set of resources. It's useful to think of a module as a sub-configuration. It has input and output variables, and modules are written in HCL. HashiCorp and open-source contributors maintain a large library of modules for Terraform users. Modules can vastly simplify a configuration by reducing the number of lines of configuration needed to execute complex configurations. AWS modules are available for VPCs, EC2 instances, and EKS, which is managed Kubernetes, and many more. Terraform modules cannot be deployed by themselves. They have to be declared in a root module. All configurations have a root module. The root module contains the resources declared in the .tf files of a configuration. External modules that are declared in the root module are called child modules. Child modules are imported into the root module using the module HCL declaration. A module declaration in the root module sets values for any input variables the child module may have. By default, child modules inherit the settings of the provider or providers in the root module. This can be overridden in cases where a module has particular requirements, like a specific provider version. There are several options for storing modules where Terraform can find them: the local file system, GitHub, a generic Git repository, HTTP URLs, and the Terraform registry. The Terraform registry is a free public registry of modules maintained by HashiCorp. Let's take a quick look at the registry. Open your browser and navigate to registry.terraform.io. As a Terraform user, you can use the Terraform registry as a central repository of public modules. You can also upload your own public modules to the registry by creating a GitHub repository, then linking it to it from the registry. If you want to share private modules with the team, you can use Terraform Cloud. We'll talk more about Terraform Cloud later in the course. Let's take a look at the module we'll be using in our exercise. We can find the verified, community-supported AWS VPC module by searching the registry for VPC. The registry entry points to the source in GitHub. The README file in GitHub includes documentation on the behavior of this module and its input and output variables. Let's move on and take a look at this module in action. In previous exercises, the VPC resource has been declared as an AWS resource type. This exercise uses the VPC module to define our VPC. We'll see that it does a lot of work in very few lines. Let's look at the VPC module declaration and break it down line by line. First, open the 02.11-12 modules folder. Copy and paste the terraform.tfrs.backup file. Paste a copy back into this folder. And then rename the copy to terraform.tfvars. Copy the AWS access and secret key either from a previous exercise or from the file you created in the AWS setup video. All we need is the access and secret key. Save the file, and in the terminal, change directory to 02.11-12 modules folder and execute Terraform init. If I scroll up, you'll notice that we didn't just download the provider this time, we also downloaded the VPC module. Now return to the main.tf file and find the module declaration for the VPC here on line 62. The module declaration starts with the keyword module, then a local name for that module. The local name can be anything that makes sense to you. It's not predefined. The first value in the module block here is the source. External modules are stored outside our configuration, so their location must be defined. This source indicates the VPC module on the Terraform registry. Modules that are stored remotely are downloaded along with providers, as we saw a moment ago when we executed Terraform init. The name attribute is optional unless we're defining multiple instances of the same module type. For example, if we wanted to define multiple VPCs in this configuration, we could add additional module declarations as long as they each have a different name attribute. The CIDR parameter sets the address range for our VPC, as we saw in previous examples. The AZs parameter here is where things start to get interesting. You may remember that subnets must have an availability zone designated so that AWS knows in which AZ to create the subnet. The VPC module allows us to define a list of AZs and handles the creation of the subnets for us. Here we have 3 AZs defined in a list, all the zones in the US2 region. The next 2 parameters are lists of CIDR ranges. The VPC module will create one subnet for each range defined in the list. The public subnets variable here will create 3 public subnets. The private subnets variable here will create 3 private subnets. Resources on the private subnet must use a NAT gateway in a public subnet to communicate with the public internet. The VPC module will also create each subnet in a separate AZ. The AZ's public subnet and private subnet attributes are related to each other. The first subnet in the subnet attributes will be created in the first AZ, the second subnet in the second AZ, and so on. The next 2 lines determine how the NAT gateway is set up. Enable NAT gateway will create a NAT gateway. Single NAT gateway will create one NAT gateway for all of the private subnets. The opposite of that configuration is one NAT gateway per AZ, commented out here, which will create a NAT gateway in each of the AZs listed. You may remember from previous exercises that public internet access requires an internet gateway, routing table entries, and associations. Using the VPC module, we don't have to worry about that. All those resources are created and handled by the VPC module. That's part of the power of modules. They can do a lot of work just by setting a few input variables. This is the beginning of a highly available configuration. AWS availability zones are completely independent from one another, with no shared power, network, or storage. Separating the resources into different AZs adds reliability. If one AZ goes down, the infrastructure created in the other 2 are available to take the load. Using the VPC module, all this is possible with just 8 lines of configuration in the root module. Reducing the length of the main.tf file is a good thing. Less code is better because it's less code to maintain. However, code reduction is really just a side effect of the true goal of modules. That is, cleanly structured code with clear separation between major elements of a configuration. A well-designed configuration should have as few resource declarations as possible in the root module. Most of the work should be delegated to child modules. That's not to say we have to go overboard. It's okay to have some resource definitions in the root module. We just want to keep most of the configuration isolated where we can. Using modules to organize the configuration makes it much easier to maintain and extend when necessary. Let's go ahead and deploy. Go to the terminal and execute Terraform plan-out equals s1.tf plan, and then Terraform apply s1.tf plan. When the deployment is complete, go ahead and play around with Terraform show and Terraform show s1.tf plan to inspect the state in the plan. Take a look at the resources that have been created. Then when you're finished, don't forget to execute Terraform destroy to clean up. Using Terraform in a real-world situation is very much like developing software. It's a team effort. Typically, operations teams have multiple Terraform users. Those users contribute to and deploy Terraform configurations. Multiple users work on the same configuration at the same time. Terraform supports a collaborative workflow through its remote state feature. When a Terraform operator runs Terraform apply, Terraform creates 2 files, one for lock and one for state. The lock file is used by Terraform to prevent 2 instances from executing an apply operation simultaneously, which could lead to an unknown state in the target provider. The state file provides Terraform with a mapping between the representation of resources in the configuration and the actual resources that are deployed. By default, these files are stored locally in the root folder of the configuration. This works well for a simple configuration that is maintained and applied by a single operator, but it can't scale to multiple operators. Multiple operators can work on a shared configuration by storing the state and lock files in a centralized location. That central location is remote in the sense that it is separate from a local configuration. Any Terraform configuration can be set up to read and write its state to and from a remote store. A remote state store used by Terraform is called a backend. Terraform supports several backends, including etcd, Consul, Postgres, and several more. We're using AWS to demonstrate Terraform, so we'll demonstrate remote state using the S3 backend. The S3 backend uses two AWS resources, S3, the simple state storage feature of AWS, and the DynamoDB database feature. When configured to use the S3 backend, Terraform will store the state file in an S3 bucket designated by the configuration. The DynamoDB database table is used to store the locking data. In the exercise, we'll take a look at two configurations, the backend configuration and the infrastructure configuration. I'll demonstrate how to use Terraform to deploy the backend resources. Then I'll show how a remote state configuration deployment differs from one that uses local state. In this exercise, I'll demonstrate how to deploy the resources required by the Terraform S3 backend. When the plan and apply Terraform commands are executed, the Terraform CLI evaluates the backend configuration before it generates a plan or deploys resources. This means that the backend resources, the S3 bucket and the DynamoDB table, cannot be deployed with the configuration that uses remote state. The bucket and table must be set up before a remote state configuration can be deployed. You could create the bucket and table manually through the AWS console or the AWS CLI, but you're a Terraform operator. Why not use Terraform? We absolutely can and should use Terraform to create these resources that are required by the S3 backend. Open the Remote Resources folder in the 0302-3 Remote State folder. Here we have a configuration just for setting up the S3 backend. This configuration will only have to be deployed once. To create the bucket and table, the S3 backend needs to store the plan and state. Our first job will be to deploy this configuration, then we can move on to the infrastructure configuration. Open s3backend.tf. We can see that it looks a lot like the configurations we've seen so far. Here we have the usual AWS credential variables and the AWS provider. We've seen a data resource before. In previous exercises, we used it to get data from AWS about availability zones and AMIs. In this case, we're retrieving data about the Terraform user we created in the AWS setup video. We need the ID AWS assigned to that user in order to refer to it in this configuration. The next resource is the bucket. The name of the bucket will be assigned to the default value of the variable for var.bucketName, which is red30-tf state. Force destroy equals true will allow us to destroy the bucket even if it contains locked files. ACL equals private designates this as a private bucket, which means access is restricted to authorized users. Versioning enabled means that data in this bucket is versioned instead of overwritten. The policy setting here is set to a text value using the Linux heredoc syntax indicated by the less than EOF string. This is a JSON formatted AWS IAM policy. It grants read and write access to the Terraform user so that it can read and write to this bucket. Note the $curly brace syntax here. This is called string interpolation, which injects the resource name of the Terraform user into the text of this policy. The AWS S3 bucket public access block resource creates an administrative override setting that blocks any public access to this bucket. The bucket will contain sensitive data, so with this resource declared, the bucket cannot be read without authorization, even if someone accidentally grants a public read policy on the bucket. The next resource is the DynamoDB table. By the way, table in this case is somewhat of a misnomer. DynamoDB is a NoSQL database, so technically we're defining something more like an object schema. This resource defines a single attribute table with one attribute called lockID. The S3 backend needs a table with an attribute with that exact name, lockID. The data type of the attribute is a string. The last resource here is the IAM policy that grants read-write access to the Terraform user so it can read and write to the DynamoDB table. Let's deploy this configuration. Copy the terraform.tfrs.backup file from the parent folder into the remote resources folder, and then rename it to terraform.tfrs. And then copy in the AWS access key and secret from a previous exercise or from the file you created in the AWS setup video. Save the file, and then in the terminal, execute terraform init, and then terraform plan -out equals backend.tfplan, and then finally, terraform apply backend.tfplan. Let's take a look at the resources we created in the AWS console. In the console, go to the DynamoDB section. Go to Tables, and open the table we created, red30-tf state lock. You can see that it has the lock ID attribute that we created in the configuration. Now go to the S3 service and select the bucket. When we deploy the infrastructure configuration, we'll see plan files in this bucket after we deploy. Let's see how we deploy a configuration that uses remote state. First, we need to make sure our backend resources are deployed. If you completed the exercise that deploys the backend, you can kick back for a moment and watch as we review the process. If not, follow along as I demonstrate how to deploy the S3 bucket and DynamoDB table needed by the S3 backend. First, open the 0302-3 remote state folder and open remote resources. Copy the terraform.tfrs.backup file into remote resources and then rename it to terraform.tfrs. Copy the access key and secret from a previous exercise or from the file you created in the AWS setup video. Then in the terminal, execute terraform init, and then terraform plan -out equals backend.tfplan, and then terraform apply backend.tfplan. I've already executed these commands here, so I'll just skip over them. Once these resources are deployed, we can move on. Now open main.tf in 0302 remote state. The very first declaration here is a portion of our backend configuration. The backend is declared here in a Terraform stanza declaration and is declared as the S3 type. There's way more to configuring the backend than just this, but the additional configuration data are sensitive, so it's best not to include them in the file. The attributes that are not defined in the configuration file here can be defined on the command line instead. This is referred to as a partial configuration. The command to deploy this configuration is in commands.txt. The difference with remote state deployment is mostly in the init command. Backend configuration attributes can be defined when a configuration is initialized so that they don't have to be persisted in the configuration file. This is more secure and more flexible because you can define the backend configuration at deploy time rather than having the bucket and table settings hard-coded into the configuration. This init command includes the parameters we need to set the backend configuration: a bucket name, the name for the key used in the state object, this is like a path to a file, the region in which the backend resources were created, and the name of the DynamoDB table where the locking data will be stored. Copy the AWS key and secret into the command, so go to terraform.tfrs, copy the key within the quotes, return to commands.txt, and select everything including the curly braces, paste it in, and then repeat that with the secret. Don't include the quotes, and do include the curly braces. In the terminal, go up one folder, and then in commands.txt, copy the entire command into the terminal. Hit enter, and we're initialized. We're using the VPC module. This infrastructure configuration just deploys a VPC for demonstration purposes. We've initialized the backend, and we're ready to move on. All right, before we generate our plan, we're going to need a TFRs file here in this folder. So copy the terraform.tfrs file from the remote resources folder into the remote state. And it should already have the access key and secret. Now we can generate our plan. -out equals s1.tfplan. And now I'm going to apply the configuration here. And while it's applying, I'm going to open a second terminal and show you what happens when two applies attempt to operate on the same configuration at the same time. So Terraform apply s1.tf plan. And then as soon as that starts, I'm going to create a new terminal here. And I'm going to change to that directory 0302 remote state and try to do it again. We get an error here because Terraform sees an active lock in the DynamoDB table. The second apply command reads the active lock in the DynamoDB table and halts the execution. This is especially useful when using Terraform with an automation platform like Jenkins or Terraform Cloud. This prevents multiple operations from creating duplicate resources in the target provider and corrupting the state. So we'll return back over to our other terminal, and we're still deploying. We'll give that a moment. All right, now that this is complete, we can go to the AWS console and look at the data that was created. If we go to the S3 bucket, we can look inside this bucket here, and we can see we have something that looks like a file system. And here's the app.state data that was created. We can also go to DynamoDB, go to tables, go to our table, and look in the items. And we can see some data here left over from the log file. So the remote state feature of Terraform supports a multi-user collaborative workflow that will preserve the integrity of deployments when executed manually or via automation platforms. Let's return to Visual Studio Code and clean up. This time we have two different configurations to destroy. It's important that we execute the destroy operations in the right order. First, we're going to destroy the infrastructure deployment, then we'll do the S3 backend. So, in this folder, Terraform destroy. Enter yes. Now our infrastructure deployment is removed. We can change to remote resources and execute Terraform destroy once again to remove the S3 backend. Once again, enter yes. And our DynamoDB table and S3 bucket are removed. We're all cleaned up. As Terraform configurations grow in size and complexity, they can become difficult to maintain and modify. There are several techniques that can be used to manage configurations to make them easier to read and to make changes when necessary. So far, we've been using a single file to store the entire configuration, main.tf. This works for simple configurations. However, production configurations are much larger, with many more resources. That single main.tf file will grow fast. You'll find yourself using the search feature of your editor to find resources and sections. That's not very efficient. We can do better. Open the 0304 complex chapter in your exercise files, and you'll see a difference in the layout from previous exercises. The main.tf file has been broken into multiple .tf files, each with a name that describes its contents. Terraform will combine all files with the .tf extension when you execute commands such as validate, plan, and apply. All these files are part of the root module of this configuration, and Terraform will deploy the resources defined in them as if they were all in a single file. This gives you as much flexibility as you need to separate the configuration by resource type or any other mechanism that makes sense to you. I've separated the files here by resource type, so each file only contains one type. So we have the data sources in datasource.tf, an EC2 instance in the instance.tf, the AWS provider, security group, and so on. The steps to deploy this configuration are exactly the same as all earlier chapters except for the remote state configuration, which has some extra steps. This configuration uses local state, so you won't need the remote state commands. See if you can remember how to deploy this configuration. Pause the video and try to deploy, then return and we'll walk through it together. If you decide not to return for the walkthrough, don't forget to remove the deployment with Terraform destroy when you're finished. All right. So we're back, and let's try to deploy. So first, change directory to 0304 complex. And then, well, before we execute anything, we need to copy in the terraform.tfvars file. So you can get that from a previous exercise. Find terraform.tfvars with the access key and secret. Copy it, and paste it in. Alternatively, you can create a copy of terraform.tfvars.backup, paste it back into the complex folder, rename it to terraform.tfvars, and copy in the access key and secret. Now we can execute Terraform init with no parameters, and then Terraform plan -out equals s1.tf plan. And finally, Terraform apply s1.tf plan. After the apply is complete, we could use the console, or we could try the AWS CLI to check that our configuration was deployed. Let's try the CLI. Execute AWS EC2 describe -instances --query reservations. That's an open quote reservations, open square bracket, close square bracket, dot instances, capital I, open close square bracket, instance ID, close quote, --output -table. This will output our information about our EC2 instances to the console here in a table. And there we have the instance that we deployed. Hit Q to exit. And as always, let's remember to clean up afterwards so we don't run out of free time. Terraform destroy. Enter yes when prompted, and this configuration will be removed. The software delivery lifecycle begins with developers committing code to a central repository where continuous integration practices trigger tests in a series of shared environments. The development environment is where new code is first integrated. The next environment may be called staging or QA, where more advanced testing is performed, such as user acceptance and systems integration testing. Finally, fully tested, feature-complete code is pushed to a production environment where it's used by end users. Terraform gives operators the ability to apply this same lifecycle to infrastructure. A Terraform configuration can be modified, tested, then the modification can be promoted through the same series of environments. A well-designed, multiple environment configuration can define a common set of resources shared by all environments and use variables to represent their differences. Such a configuration must be split so that changes can be made to one environment at a time. The infrastructure of the environments is often slightly different. For example, to save cost, development environments are usually not redundant in the way that production environments are, and they use lower capacity resources. In Visual Studio Code, open the 0305 to 6 multi-environment folder. This configuration is organized differently from the ones we've seen so far. The environment-specific files are stored under the Environments folder. Each environment folder has a separate provider.tf. This is to handle output variables. Each environment has a dedicated .tf-vars file. Remember that Terraform will use any local file that ends in .auto.tf-vars. All the commands to init, plan, and deploy will be executed in these environment folders. If we look at the tf-vars file, we can see they're slightly different from each other. This development.auto.tf-vars.backup, which we'll use in the exercise, has an instance count set to 1, and the instance tag is set to development. Here in QA, the instance count is set to 2, and the environment tag is set to QA. And finally, in the production tf-vars file, the instance count is set to 4, representing a full-sized, load-balanced production environment. The common files of the configuration are stored in the manifest folder. This should look familiar. We have VPC definitions, instances, security groups, etc. This organization allows an operator to deploy each environment configuration independently. Changes made to the common configuration in the manifests folder can be deployed and tested in dev before they're then promoted to QA and then finally production. Let's demonstrate the deployment process of this multi-environment configuration. In the terminal window, change to the environments/0_development folder. They're numbered to display them in the order of deployment. Now execute cp development.auto.tf-vars.backup development.auto.tf-vars. This will create a copy of the backup file and rename it so that we can copy in our AWS credentials. Open the file here in Visual Studio Code and copy the access key and secret key from a previous exercise. Then you'll want to set the region. I'm using US East 2. The commands to deploy are similar to the ones we've used in the past, with a few additional parameters. The slight difference is that we'll execute the commands from this folder, and we can tell Terraform where to look for the rest of the .tf files, which are in the manifests folder. Execute Terraform init //manifests. This is the path to the remainder of the configuration. And now that that is complete, we can see that we're initialized and we have our .terraform folder under the 0_development. We can also see, if we look in manifests, that that folder is unaffected. Now we'll generate a plan. Terraform plan -out equals s1.tf plan, and then once again, the path to remainder of the configuration. And we have our plan generated, and now we simply apply s1.tf plan. All right, now that we're deployed, let's check our work. This time we'll use the AWS CLI instead of the web console. Open the commands.txt file and copy this first command into the terminal. This will disable paging with the output from the AWS CLI. Now paste in the second command. And we see the instance that we just created. Now we'll repeat the process for the rest of the environments. So we'll go up one level and change directory to 1_QA. We're going to copy qa.auto.tfvars.backup to qa.auto.tfvars. Open the file, copy in the credentials and the region, and do our commands. Init, plan, and apply. And finally, production. All right, all three environments are now deployed. Let's check our work once again. Open commands.txt and execute this command once again. And we see we have a total of 7 instances, 1 in dev, 2 in QA, and 4 in production. You can also use the other commands here to query by tag to look at other environments. For example, we can copy this one in for dev instances, and we only see the development instance. This is a good example of how tags can be useful. You can annotate resources and discover them later by value using the AWS CLI. The AWS CLI is useful for a quick check like we're doing here. Also, if you're running this in automation, it could be a post-deployment validation step. So Terraform configurations can be developed and promoted through a series of shared environments, just like application code. The right configuration layout makes it easy to share common resources between environments. Variables and variable files define variances between environments to save costs. All right, as usual, our last step is to remove what we've deployed. So once again, you'll go into each one of these environment folders and execute Terraform destroy. And we need our parameter to tell Terraform where the remainder of our configuration is. Enter yes when prompted. Remember to do this in all 3 environment folders, and we'll be all cleaned up. We've seen examples of module usage in previous chapters. We've used the VPC module to define a complex VPC configuration in just a few lines of HCL. Cloud providers and open source maintainers create modules as tools for Terraform operators. Modules isolate complex configurations of related resources into a single composable unit. Terraform operators can just as easily create modules for themselves. Consider our use case. We have a client, Red30, with a large and growing infrastructure. As their infrastructure grows, modules will become increasingly useful to tame that complexity. The exercises we've seen so far have a common theme. Red30 uses a lot of Node.js web servers in their architecture. They routinely deploy a common cluster of resources together, EC2 servers running Node.js, in a dedicated VPC with HTTP and TLS security groups applied. This is an excellent case for a custom module. Let's take a look at our example. Open 0307 custom module. Let's prepare the terraform.tfvars file. So cd 0307 custom module, and then copy terraform.tfvars.backup to terraform.tfvars. Open the file, and copy in the access key and secret from a previous exercise or the file you prepared in the AWS setup video. And we'll set the region. I'm using US East 2. Now open main.tf under 0307 custom module. We can see that this is a short one. All we have is an AWS provider and a module declaration. The VPC module we've used in previous exercises is hosted on the Terraform registry. The source attribute defined here points to a local path, modules/node.js-instance, which is right here in the configuration. This is a good way to start developing a new module as a local module within an existing configuration. We can test it, make changes as new requirements emerge, and fine-tune it. After it has been thoroughly tested locally, it can be published to a registry. In our case, Red 30 would likely want to publish this module to a private registry as it is specific to their deployment requirements. The instance count and environment tag settings are input variables of the custom module. Let's take a look at how that module is defined. Open main.tf under module Node.js instance. These resources will look familiar. They're all the same as we've seen in previous exercises: VPCs, route tables, subnets, and so on. Open the variables.tf and outputs.tf, and you'll see the usual variable declarations. Returning to main.tf, one major difference in this module definition is that there's no provider. The provider settings are inherited from the root module. That inheritance can be overridden if necessary to enforce a version compatibility requirement so that a specific provider is used. Output variables in modules also behave a little differently. They're not output to the console, and they don't automatically become output variables of the root module. The values of the output variables are available to the root module in the same way that regular resource values are available throughout the configuration after deployment. Here's an example. Go back to the variables.tf file in the parent here and scroll down. The output variable here returns all public DNS entries for the instances we're creating with the custom module. That value is a property of the module, node_instances. If we return to the main.tf, you can see that module declaration here. Any data we want to expose from a custom module to the root module is exposed through output variables in the module. I'd like to point out another aspect of this module. Note that there are no modules defined within it. We used a VPC module previously to define VPCs, but here the VPC and all its components are declared as resources. Terraform can embed one module within another, but it's generally not a good idea. It can make configurations overly complex and lead to versioning issues between modules. The behavior of this module is quite straightforward. It allows an operator to deploy multiple Node.js web servers with environment tags, all in a single module declaration. This is a very simple module. It could easily be enhanced with more options and more resources. For example, one might want to add an option to create an AWS ELB load balancer between the instances. Also, this module could be declared multiple times in a root module to define multiple environments, or the module could be enhanced to create an arbitrary number of server groups, each with their own tags and subnet settings. There are many possibilities. If you've been following along with other exercises, you already know how to deploy. Pause the video and give it a try, and then come back and I'll review. All right, and we're back. I'm going to close all the other files here, and we are in our directory, so I'm going to execute Terraform init. And then, as usual, Terraform plan -out equals s1.tf plan. And we have our plan created, and finally, Terraform apply s1.tf plan. And here we have it. 2 instances deployed, and we're good to go. Once again, as usual, always remember to clean up. Enter yes when prompted, and the configuration will be removed. Modern software is delivered using continuous integration and continuous delivery, or CI/CD. CI/CD is a methodology supported by a set of tools to continuously integrate and deploy code as it is developed. This includes source control, most commonly Git, and a CI/CD orchestrator such as Jenkins or GitLab. Terraform configurations are infrastructure as code. They are code-based, deployable descriptions of a system's infrastructure. It stands to reason, then, that configurations should be treated the same as any other code. Thus, Terraform code can get the same benefits as application code does from CI/CD. Configurations can be source-controlled, versioned, and iterated over just like application code. Incorporating Terraform into a CI/CD pipeline can dramatically enhance testing capabilities. Source control triggers can execute tests, not just for an application, but also for the infrastructure to which it is deployed. Changes to the infrastructure definition can be tested frequently, together with changes to the application. This leads to faster discovery of infrastructure-related problems and gives operations teams the freedom to experiment more frequently with infrastructure optimizations. Traditionally, long-running test environments take up resources such as virtual machines. Application code is repeatedly deployed to development and test environments then tested for functionality and performance. Terraform can also be used to support ephemeral test environments. Rather than repeatedly redeploying application code to the same environment, test code can be deployed to newly provisioned resources with each test. The entire environment can then be torn down. This has the potential to reduce operational costs and free resources while they're not in use. Production environments can also benefit from Terraform. Constant redeployment can cause configuration drift, where side effects from repeated changes can lead to bugs and degraded performance. Terraform can help prevent that by supporting immutable infrastructure. Immutable infrastructure means that changes are never made to existing resources. Upgrades and bug fixes are always deployed on newly provisioned infrastructure. Speaking of upgrades, Terraform can help there as well. New versions of an application can be deployed to new resources without affecting existing versions and resources. Distributed applications are usually made of a large assortment of components. For example, an e-commerce application may have front-end virtual machines, dedicated HTTP servers, a microservices middle tier, and a database layer. The microservices are likely to be under active development, with frequent changes being pushed to production. Terraform can deploy services to new VMs in the service tier, and traffic can be gradually routed to those new VMs over time. If there are problems, the traffic can be routed back to stable service versions in real time. This is called a canary deployment. So, Terraform is great by itself, but it's awesome when combined with CI/CD tools. Modern DevOps practices mean that we should treat infrastructure code no differently than application code. Combining infrastructure deployment with application deployment using Terraform offers significant benefits to deployment velocity, operational resilience, and reliability. Terraform is very often combined with CI/CD orchestration platforms. Jenkins is one of the best-known CI/CD platforms. Let's take a look at an example of how Jenkins and Terraform can work together to automate the deployment of infrastructure. I'll be working with a local Jenkins server throughout this example. If you want to follow along, you'll need to start a Jenkins server on your computer or have access to one. Starting a server is quite easy. However, Jenkins setup is beyond the scope of this course. If you want to start a local server but don't know how, the Learning Jenkins course here on LinkedIn Learning is a great resource. That course offers several options to install Jenkins on a variety of platforms. You should be able to find the video in the course that applies to your platform. Complete the video that applies to you, then you can return to this video and follow along with the exercise. I'll be running Jenkins in a Docker container. First, we need to find the pipeline we'll use in our Jenkins job. In Visual Studio Code, open the 0402 Jenkins folder. You're probably wondering, where's the configuration? All I see is a Jenkins file. This Jenkins file is a declarative Jenkins pipeline. It is programmed to clone the exercise files from GitHub, then deploy the 0302 remote state example through Jenkins instead of manually. The remote state exercise demonstrated how Terraform can store the state and locking data of a configuration remotely, separate from the local files. This is especially important when using Terraform in combination with any type of automation. We'll be creating a Jenkins job in this exercise. Jenkins jobs perform a set of automated tasks as a group. Jobs can be executed automatically by external triggers or manually by a human operator. A Jenkins job that performs Terraform operations can be executed multiple times, launching multiple job instances running in parallel. This is why it's important that any configuration deployed by Jenkins and Terraform use remote state. If two Terraform deployment jobs are executed through Jenkins, the remote state configuration will prevent both of them from executing at the same time, which could lead to duplicated resources and unknown state in the target provider. In your browser, navigate to and log into your Jenkins server. It's probably at localhost:8080. Click New Item on the left or click Create a Job. Set the name to Terraform, select Pipeline, and then click OK. Now return to Visual Studio Code, find the Jenkins file, select all of its text, copy it, then return to Jenkins, and paste the script into the script field here at the bottom. And then click Save. Now we need to set some values in Jenkins. The AWS keys are sensitive data, so we don't want them in the Jenkins file where any Jenkins operator can see them. Jenkins has a mechanism that will allow us to store these secrets securely. Click the Jenkins icon at the top left, then select Manage Jenkins. and click Manage Credentials. Here we can create variables whose values will be protected by Jenkins. They will be read-only after they're created, and their values will always be redacted if output to a console or log file. The Jenkins file refers to these variables and uses them to provide the AWS credentials to Terraform. Hover over Global, click and select Add Credentials. From the Kind drop-down, select Secret Text. The secret field will be the sensitive data. Return to Visual Studio Code and find a TFRs file from a previous exercise or the file that you created in the AWS setup video. Copy the AWS access key without the quotes. Then return to Jenkins and paste that value into the secret field. In the ID field, enter capital AWS_access_key. We can skip the description as the ID is self-explanatory. Click OK. Now we'll repeat that process for the secret key. Click Add Credentials, select Secret Text, return to Visual Studio Code, copy the secret key, paste the secret, and the name will be AWS_secret_key, and it must be all caps. And click OK. Now we'll go back to the job. Click the Jenkins icon and select the Terraform job. We're ready to deploy, so click Build Now. You'll see the stages of the job proceed one at a time. This pipeline is set up to deploy the S3 backend required by this configuration, then deploy the infrastructure configuration. The infrastructure configuration just deploys a single VPC for demonstration purposes. By the way, for convenience, this example combines the deployment of the S3 backend and the infrastructure configurations into a single pipeline. In practical use, they would be separate jobs because the backend only needs to be deployed once. While the build is running, I'll very briefly review the structure of the Jenkins file. Jenkins files are written in Groovy, a language compatible with the Java runtime. The stages we saw in Jenkins are defined here as stanzas. The first stage clones the exercise files from GitHub. The next one downloads the Terraform CLI binary. A production-configured Jenkins installation wouldn't need this step. It would have the Terraform CLI pre-installed on the agents. The next several stages break up the steps of init, plan, and apply for the backend configuration, then the infrastructure configuration that deploys the VPC. The sh commands run the Terraform CLI commands as shell scripts. These commands should look familiar if you followed the preceding exercises. Now return to Jenkins. The pipeline will pause after the config apply stage is complete, waiting for input. If you'd like, you can go to the AWS console, go to the VPC section, and see the VPC. And now we'll return to Jenkins, and we see that the pipeline is complete. This pipeline will pause after the config apply stage is complete, waiting for input. If we hover over the destroy stage, we can click Proceed. This final stage of the pipeline will run Terraform destroy on the backend and infrastructure configurations. So, without a lot of fuss and trouble, a Jenkins server can be configured to execute a Terraform deployment while protecting sensitive data. This exercise demonstrated how a Jenkins file can define a pipeline that deploys configurations in stages. This simple example pipeline could be extended and enhanced to include application deployment and testing to a temporary environment. Terraform Cloud is provided by HashiCorp as a cloud-based software-as-a-service automation platform for Terraform. Operators use it to create jobs that run on cloud compute resources dedicated to generating and applying plans. Large, complex configurations can take several minutes to plan and even longer to deploy. Operators can delegate the execution of long-running Terraform commands to Terraform Cloud, thus freeing local resources and avoiding the cost of running them on paid cloud compute. There are 3 plans available with Terraform Cloud. The base plan is free. It provides an account with up to 5 users, 1 concurrent run, and support for basic Terraform commands. Paid accounts add enterprise features such as Sentinel policy support and additional concurrent runs. I'll be demonstrating the exercise using a free account. If you're following along with the exercises, you'll need to create a Terraform Cloud account. It's free. Just go to app.terraform.io, complete the registration, and you have an account. Log into your new account and leave that tab open for later. The version control exercise will require you to have a free GitHub account. If you don't have one, open a new tab navigate to github.com and create one. Log into your new GitHub account and leave this tab open as well. You'll use your GitHub account later when we get to that exercise. Return to the tab where you're logged into Terraform Cloud. When you log in for the first time, Terraform Cloud will prompt you to create a new organization. Let's call it Red 30 because, as you may remember, that's the client our fictional consultancy is working for. Enter Red 30 here and click Create Organization. Now let's take a quick tour of the Terraform Cloud web-based user interface. Click the Terraform icon in the top left. This should take you to the Workspaces section. Terraform Cloud organizes jobs into workspaces. Workspaces are used to plan and deploy configurations that are stored in source control, such as GitHub, or on local configurations through the Terraform CLI. In either case, Terraform Cloud executes, plan, and apply commands using its cloud compute resources. We'll create some workspaces when we proceed to the demos. Click the Modules tab at the top. If you've completed the modules exercise, you'll remember that remotely hosted modules can be stored in a number of places, including GitHub, the Terraform registry, and local paths. Terraform Cloud provides a private module registry for use by teams. You can add your own custom modules to a Terraform Cloud organization by configuring a VCS, a version control system. Your configurations can then refer to Terraform Cloud as the source of your custom module. Now click the Settings tab and look at the User section. If we had multiple colleagues at our consultancy, all working on the Red 30 account, we would invite them to this organization so we could all work together on our client's configurations. The free account allows up to 5 users. The Teams section here allows you to manage the owner's team, which is the default team in a free account. Paid accounts can have custom teams, so you can set granular permissions on who can execute commands for specific workspaces. In addition to the CLI, the command line, VCS, version control, Terraform Cloud also supports API workflows. The Terraform API is a RESTful API that supports most of the functions available through this web interface. This section can be used to generate an API token. API tokens are like passwords used by other systems to communicate with the Terraform Cloud API. The API makes it possible to integrate Terraform Cloud into any system that can make API calls. The authentication section offers some customization for user sessions, and for paid accounts, options to enforce two-factor authentication for users. SSH keys are used here to allow configurations to download private modules. And finally, the VCS provider section is where you'll configure GitHub when we do our demos. Let's move on.